Well, welcome everybody to the Mound Discovery Center for tonight's talk, and I want to recognize that tonight's talk was sponsored by Precision Joining Technologies. They're a small company here at the Mound Business Park. Joe Kwiatkowski and his team have been here for almost 30 years. They were among the original businesses here at Mound. And so they've sponsored this, and so if you'd like to sponsor an event or displays or donate, you can do so. Go to our website at moundmuseum.com, and there's all the information there. Tonight we've got our speaker you'll recognize because he used to do this job.
Yes. And
he handed that off. It took two of us to replace Bob, so that's how good a job he did. And so Bob Bowman is our speaker tonight, and he's going to be talking about the diverse roles of hydrogen and metal hydrides from a historical perspective. And I just want to say before I hand it over to Bob that I hope people appreciate what we have here at Mound. Bob is a great example of this. We have world experts. I mean, I've worked on projects with Bob, and people from literally around the world find his name as an expert in this technology, and they contact him. So it's kind of neat that when I have a question, I don't even have to use AI. I just use Bob Intelligence and give him a call. And that's the other remarkable thing. The guy, if you ask him a question, he'll shoot back so many documents your inbox fills.
That's right. I'll second that
one. Very efficient at that. So I'll turn it over to Bob now, and we'll enjoy the talk.
Thank you.
Well, Doug, thanks for the invitation. Turns out, let me start. You see 4 modes of transportation: space shuttle, fancy car, bus, submarine. All of those are being powered by hydrogen in one form. Still burning H2, but and I'm going to cover each of those in some level. But I give you my background so you know. I've been involved in metal hydride technology for over 50 years, starting here at the Mound Laboratory back in 1969. And then that was when I was working on lithium deuteride tritide and other materials that went into nuclear weapons. I transitioned to other things over the years, but that's what I started in. And I worked for the aerospace company, Aerojet Corporation for a while, Jet Propulsion Lab for a little over 11 years, Oak Ridge National Lab. I did an off-site visit at University of Utah. So you see, I can't keep a job. The problem is, I want to do hydrogen metal hydride, and sometimes people would want me, and then those projects go away, and I did other stuff. Some wasn't very pleasant. One of the things at JPL, I got to play with real rocket fuel and test burns and stuff. But not everything's like that. Sometimes it's dull. But anyway, but I've looked at and involved in a lot of materials a different way. So we're going to start with hydrogen. You know, if you remember your periodic table from high school or college chemistry, that's number 1, the first element. It's also the most common element in the universe. There's a lot of hydrogen. It's also the lightest, 1 atomic mass unit, and least dense gas. Now there are isotopes, deuterium and tritium. Those are the ones that do fusion and are in fusion power and lots of nuclear weapons stuff. Hydrogen is 13% of all the atoms on Earth, and but it's only 0.75% by weight because it's only 1, and other stuff weigh 20 or 30 or more. The hydrogen atoms are extremely reactive, and they've virtually always formed in compounds. First, pure hydrogen, H2 molecule, light and flammable, natural gas, methane, CH4, and then water, ice, steam, everywhere. And so that's all hydrogen. And another major product is ammonia. Ammonia not in our environment, but it's an important industrial chemical. Now most hydrogen, and I really mean most, comes from a chemical reaction of reacting methane. Let's see if I find the right button here. Methane with water and mix it. And what you'll get is carbon dioxide and hydrogen molecules, and then the hydrogen molecules, something you've got to do with and use. Now, we're looking at fuel. I'm going to go in and out about fuels, but this is looking at gravimetric and density on the x-axis. Wrong button. Gravimetric here, and this is volumetric. Those are very important for your fuel. If you got to carry a lot of mass for what you do, or you put a lot in a confined space because you don't want a big volume to go. So if you look here at the diesel fuel and lots of others, their gravimetric's not very good, but they can have very high density. Hydrogen, on the other hand, by mass, whether it's a liquid hydrogen or high pressure gas center bar, it has high gravimetric but very low volume. And what you want is, for future target, this would be the ideal range you would get. That's a big challenge because you can't just move there to get it where you want it. The other thing about hydrogen is, I told you before, most of it is made chemically, and that's a process called gray hydrogen by steam reformation from natural gas. What happens is you make the hydrogen, but you also have carbon dioxide. That causes global warming. And so if you dump that, that's gray. If you can make hydrogen from coal, and that's black, but that has even more impurity, sulfur and other things that come out. If you do steam reformation and capture the carbon dioxide, quote, store it somewhere or chemically react it, you get blue hydrogen. But the holy grail is green hydrogen. When you get electrolysis, you just split water into H2 and O2, put the hydrogen to store and oxygen to do. So that would be now you can make it by nuclear power. That called pink hydrogen down here. And there's a recent discovery plan that inside the Earth's core, that's actually, it's liquid iron hydride. But it's, it's a few thousand miles down in there. But they're talking about maybe you can mine that and get lots and lots of hydrogen. I don't know, but anyway, it's getting some talk about in recent times. So, and this is a data source I had a couple years ago about most of the hydrogen comes from reforming, and some from coal. Natural gas is 48, and so this is production, and then this is consumption. A large amount is used in making ammonia. Ammonia is a very important feedstock, fertilizers and lots of other things. And if you look for electrolysis, all kinds of electrolysis, it's only about 4%. And the intent is that you like it to be more, and particularly to take over to replace coal and so forth and natural gas. Now, here's space. This is anything hydrogen used in space. And you see it's very small. But on the other hand, that's a lot of technology and useful science stuff that came. So I'm going to emphasize this a lot more than that. So it's constant. And so we're talking about how hydrogen is used. It's used for both transportation and, as I said earlier, the chemical industry, refineries for processing petroleum, ammonia production, steel, have used massive amount of hydrogen. But again, they get it from natural gas. They still have CO2. And that's not what I really wanted to cover. And so here's kind of a chart. You see different configurations of rockets. And I have launch vehicles, various types, power system, fuel cells, and nickel hydrogen batteries. Actually, and sometimes hydrogen has been used to make water on spacecraft, like space shuttle. And reference gas was an example. A gas-gap heat switch is a way to have thermal isolation conductivity. The reason I put those, these are places that metal hydrides have had a role in doing that. And cryogenic cooling, you can have Joule-Thomson cooling, because you take hydrogen and you can make liquids, and now you have a cooling source. And there was an area that we worked on, absorption cryocoolers, which I will talk about, that produced cooling for on spacecraft to do things. It can be used in many other applications too. And there's been looking at various roles in spacesuits or what they call in situ, going to planets, using hydrogen as a means to convert gas that you find, like on Mars, into oxygen and so forth. So there's been lots of interest of hydrogen space over the decades. But it, as rocket fuel, has really been the big user in space. And here's the, and it burns. It basically reacts with oxygen. And they have been using, oh, wrong button again. They've been using hydrogen to launch spacecraft since 1963. And the liquid hydrogen and liquid oxygen are both cryogenic rocket engines, and where the liquid hydrogen is the fuel and reacts with liquid oxygen. And what they have is, this is your rocket equation, which tells you how much lift you get, and the parameter is, the larger this number, the better it is. And burning hydrogen and oxygen gives you in a unit over 400, 460, where if you do a solid fuel, it's lower, and kerosene, and liquid oxygen stages. So this has happened to be one of the space shuttles that was launched, so burning hydrogen as it goes off. And these are a collection of vehicles that have been using hydrogen. The NASA program, you know, Saturn V, and the ones with X's are SpaceX. They don't like hydrogen. Elon Musk has a thing against hydrogen, as he does with a bunch of other things. So he uses methane, and it works. But the Soviet Union, Russia, NASA, ESA have used hydrogen to launch their vehicles literally for decades. Now this is the space shuttle. The launch. This is the where you have the shuttle ride. Shuttle rides on the launch vehicle. It's a reusable. In the launch, they'll burn 230 kilograms of hydrogen. That's a lot of hydrogen. And so, but it was used in space shuttle for over 30 years, and they have three engines that burn liquid hydrogen. Did 135 launches with 2 failures. We know they lost the astronauts when those occurred. But so that's been a and if I go to the next slide, so this is where the liquid hydrogen is stored in large complex at Kennedy Center, and with all the relation, because you make the liquid, you got to keep it cold, and so it's expanded to large scale, but it's also very expensive. So it kind of limits what one can do. But there are a role for the metal hydride, and I will describe metal hydrides a little further, but they are also used in solid state rockets. And the advantage there is, for a certain system, you'll take a metal, and one example that's been used quite often is alane. That's aluminum H3. Because not only when you react it with oxygen do you make aluminum oxide, you also make water. So when you do that, it goes through the process of making the propellant and burning it, you get more lift than what you get if you just burn aluminum metal. Aluminum metal is in a lot of propellants, and as the agent reoxidize, give the heat. And there have been other metals too that have been looked at over time. So you get, by putting a little hydrogen in, you get more lift than you get without it. Now, there's also been on-board use of hydrogen. That's for fuel cells. You've heard about fuel cells. Well, NASA has been using those for over 60 years. And there's two types, well, there's several types of fuel cells that exist. I kind of list here alkaline, which is potassium hydroxide, and PEM, proton interchange member, and with a polymer. They're going to do methanol, phosphoric acid, and solid oxide. But ones that have actually flown on the space shuttle or mission have an anode with H2, and it reacts with oxygen, with a current flowing across here and collecting making the water in here. So it allows you to generate power fairly efficiently. And this is actually a photograph. These are Apollo fuel cell. I went down to Florida for a trip, and these are on exhibit down there, so I took a couple of photographs of them. So the Apollo mission, they used 36 kilograms, and that was in the spacecraft where the astronauts were. And the shuttle mission, because they were longer lasting, used up to 210 kilograms of hydrogen to produce the power. And so these, another alternative, particularly for long duration flights, as we're not manned, is nickel metal hydrogen. This is a reaction between nickel oxide and hydrogen gas to form nickel hydroxide. And so you have canisters of high pressure gas that will react and produce power. This is really works well back when they needed a lot of load. Now, these were used early in the 60s and 70s, but with the development of lithium-ion batteries, they have replaced them. So in the last decade or so, most like the space shuttle now use lithium-ion, but these were the baseline technology for providing the electrical power needed on the space shuttle. Now, I'm going to talk a little bit about how metal hydrides are used. I'm going to, in a few minutes, describe how it works. But the first use of metal hydride was actually in a attachment to the mission that went on the Cassini mission to Saturn in early 2000. And there was a probe called Huygens. And the Huygens probe went down, it launched in 97, flew. And what it did, this probe was descended to the atmosphere, and they had a gas chromatograph monitoring what the gas was, because they had no idea what the composition of the atmosphere was. And so they used a hydrogen reference carrier gas to run through the GCMS, gas chromatograph mass spec. And so it was used, and what they needed is they needed a fair quantity of hydrogen, not a large quantity, but in a very small space. And what a company in New Jersey did is they developed a metal hydride, a rare earth hydride that had 57 grams of alloy, would store 7.5 standard liters. And so these were put on the system. They're shown down in here somewhere. I can't see it from this angle. But they were used for that mission. So they started in the 90s, was used in the early 2000s. Another application, in which I mentioned here, is absorption cryocoolers, where metal hydride is basically based on the Joule-Thomson effect. Joule-Thomson is that if you expand the gas from high pressure to low pressure, in the process you will cool the gas, it will lose energy. And so, and metal hydrides have reversible cycles. And this was work that was initiated at JPL. I wasn't involved in the first phase, but I did support 2 missions there. So I worked on the desorption, helped design and configure the second one, which I'll talk about. And this is an example of one that I worked on where we used 2 different hydrides. The intent was for a spacecraft called Betsy, at the Brilliant Eye Tensorption Cryocooler experiment. This was initiated back in the Star Wars days, when they were concerned that the Soviet Union might send missiles over, and how would you track them? And when they get out of the atmosphere, they cool down. And so normal infrared, high frequency can't monitor, but low frequency infrared will. But the detectors need to be cooled down to the order of 10 to 15 Kelvin in order to detect that radiation. So the scheme was to actually use pressurized gas that would expand into the absorbent bed, and then here would be it would cool at the JT valve, and it was used on, it was flown in the space shuttle in '96, and it did work because they used a second hydride we got down to about 22 Kelvin with liquid hydrogen. Then we closed that valve and opened a lower pressure absorbing hydrogen, zirconium nickel. And that dropped the pressure down to torr. And that caused it to freeze in place. So now you had a cold temperature that you could use. And so, but the thing was, the Soviet Union collapsed. And all of a sudden they didn't need Star Wars missiles, so it never went beyond that flight experiment. But we learned a lot, and so here it is when it's on the space shuttle. And we actually got solid hydrogen at 11 Kelvin. And again, this was mounted on the space shuttle Endeavour, and it was mounted on the sidewall, so you can see the picture here. And it was used, there were hydride beds, there was two lanthanum nickel tins, and what they did is they absorbed the gas and then pressurized it. And this is the cooling chart measured at the sensor. So the initial cooling was down to liquid hydrogen in the low 20s. Then when they opened the zirconium nickel bed, it dropped and formed a solid. It stayed cold for several hundred seconds. And this is the seep as it's cooling. So that pressure drop allowed you to make lower temperatures. Because of what we did, there was a science mission out of Europe, European Space Agency. And this was a mission called Planck, for Max Planck, the Nobel-winning about background radiation, because he's won the infrared frequency of radiation. And it was to measure the cosmic background radiation. That's the remnant light from the Big Bang. And they wanted to get measurements at lower frequencies than they could get with other ones. And in fact, the 2006 Nobel Prize went to two of the scientists involved in a program where the Planck mission was part of it that produced the data. So, I'm a third cousin to a Nobel laureate, kind of. Maybe fourth cousin, I don't know. But, so we had, they had used a high frequency, which is longer, had the 10th Kelvin. We got the 10th Kelvin by condensing helium-3, but that needed to be pre-cooled with liquid hydrogen. And these were low frequency were radio receivers cooled at 20, and the peak of the black body ratio, so you needed 2.7. And so the data was collected, it was flown, and the satellite was put in a position called L2. L2, here's the Earth, there's the Sun, and the L2 position is where the Planck satellite went. What it does is the Earth blocks the sunlight. So when it stares out into deep space, all it sees is the cosmic ray. You don't see sunlight or from other things popping up. So they took that data and plotted it and did lots of stuff with it. So it was fairly sophisticated. It had these step core. They used the absorption cryocore to make liquid hydrogen at 20 K. Then they used a mechanical refrigerator to make helium-4 to get down to 4K, and then they used the helium-3, helium-4 dilution refrigerator to get them down to a 1/10 of a degree Kelvin. So they went from ambient temperature to a 1/10 of a degree in 3 stages, and then this was continuing operation. We had, in the case of hydrogen, we had a series of bits. So this is a schematic showing all the parts of the metal hydride bed and how they would circulate through there. Anybody's interested, let me know. We have several papers that describe it in detail. And so we built two these core units. They were put on the spacecraft, and it was tested, and then it was launched in 2009. And with the combination of the two cores, it took all the data that we needed. They were able to manage the thing and the measurement, and it lasted for from 18 months to actually 50 months. They continued collecting data, which was useful to cross-check. So those are the uses of hydrogen in space. But other area that has really been in fashion the last few decades is clean energy. And hydrogen, since it turns into water, whether you do an electrochemical reaction or you burn it, is that if you have pure hydrogen, you're not going to have pollution. It's getting the hydrogen pure that is a challenge, but and so various means of transportation were done. And so, the cleanest way is solar, and one way is to use direct solar panels into batteries. And among the batteries, there are nickel metal hydride batteries I'll talk about in a few minutes. But there's also fuel cells where you can make hydrogen from solar energy to capture the hydrogen, separate hydrogen from water, store the hydrogen, distribute it, pump it into a car and store it either in a gas form or in a metal hydride, and use it for transportation. And so for the better part of 40 years, it's been looked at off and on at various levels. So the thing is, because the technology for battery was very straightforward. The batteries were heavy, but they were, and so battery electric cars are really the primary way, although there are plug-in hybrid cars that are part there. But so it was easier to implement because of structure. But fuel cell vehicles weigh less, take less space. So in principle, we have a lot of options, but it's not as energy efficient and easy to implement. And so it really, and the big thing about the lithium-ion batteries kept being improved a lot from what they were initially. And so but there are still nickel metal hydride batteries that are used. And again, this is a little collection of schematics about how what were wanted for cars. They wanted for a gas station to have how much gas you could store per unit volume. That's part of the thing. And these targets are very demanding, very high. And so if you wanted to get 700 bars, would only take you to about 40 grams per liter. And that's very high pressure. And so to get up here, it's just not feasible to do that. And so, but this is 700 bars were straightforward, and so they have been built and used in vehicles. But the other thing is they use solid materials that, and you have absorption, which is chemical absorption, and adsorption with a D. I found this cartoon years ago, and I've always liked it. So this symbolizes adsorption. A piece of pie that you swallow goes inside. Good. This is what happens when you have adsorption. It sticks on the surface. So I think they get the message across. And so you need a lot of surface area to store a lot of hydrogen. And so, and you would like reversible. That is, put the hydrogen in, use it up, be able to put it back in. And so many metal hydrides are reversible, not all of them. And adsorption is reversible too. Non-reversible is you convert chemically. It's like this is aminoborane or isoalcohol. You can reform gas and make it, but you don't get to convert it back. So it's not very, very practical. Let's see, I think I have two. Yep. So these are the kind of volumes that you would get. And so if you had 1 atmosphere of hydrogen to store, it's 1/10 of a gram. So this is actually, to put it on scale, each dimension has to be 4 times larger. And if you go to 150 bar, like lab cylinders are, you go to 10 or 350 bar, this is 700 bar, you get about 40. Liquid hydrogen is really condensed, but now it's super cold. And so any heat gets in, causes it to boil off, build up pressure. Now, the thing with metal hydride is theoretically, they can put the hydrogen in the lattice, you can get pretty high density from 100 to 150 grams. And those are different magnesium hydride. The problem is when materials are not compacted in the lattice, they're actually are powdered and so forth, so they take up a lot more space. But, you know, water stores a lot of hydrogen, over 100. Okay. All right. So, as I said earlier, compressed gas has been the way. That gas cylinders are very heavy and bulky, and there are carbon-wrapped metal Type 3 tanks which have been developed, and Type 4 which are lighter. These are fiberglass, and they have been put into vehicles. This is a GM project from about 12, 15 years ago, where they had a compressed hydrogen tank. The trouble is, they're pretty large because you've still got a limited density that you can get, and you need the outside container. But they're relatively straightforward to implement, and many demonstration cars through the first decades of the 20s used hydrogen range. And these are just examples. Mercedes-Benz, Toyota, Hyundai, all these showed that you could deliver the range under many conditions, but it was still impacted the amount of transport you could do, and there was still the issue of filling up with high pressure hydrogen when you run low. And so this is a schematic, and I think I got one more that comes in. So this is where cute from gas. I think it's cute. I don't see that. This is if a metal reacts with hydrogen gas, you can form a hydride and you release heat. If you can make it electrochemically by adding an electron, you can make a hydride and hydroxide in solution. So you can form hydrides a different way. And basically what the hydride is this is a metal lattice, and you have hydrogen molecules that absorb or stick on a surface. With chemical bonding, they'll separate them, whether it's from gas, H2, from water, and they actually break the bond that goes into the lattice. There's chemical bonding of different type. And so you can store a fair amount of hydrogen in the environment. So these are some examples of hydrogen storage hydride system. They got the name beds because they kind of lie there. But anyway, it's been in nomenclature for a long time. And again, so the way you characterize it is that the amount of concentration of hydrogen absorbed, normally you have a metal, a little bit will dissolve, and then you form a hydride with some. And in between, as you go between phases from the Gibbs phase rule, pressure stays basically constant. So you have a region of constant pressure, so you can either fill or absorb. However, as the system goes up in temperature, the pressure goes up, and there's a critical point thermodynamically where it'll go in, but it won't phase separate. The thermodynamics are shown by a log plot of temperature, so you get the entropy and the enthalpy. So you can use those parameters to characterize different storage systems. And so this is kind of the ideal behavior. Real materials have, you see these are flat, and the pressures are, well, there's hysteresis. It takes more pressure at a constant temperature to put hydrogen than it does coming out. It has to do with there's strains formed in the material and so forth. And so there's changes in composition. So real material, and they vary depending on the material and structure, how they behave. But and then, so all those are impact problems. But they've been looked at. I'll show you a couple more examples. But one area where they're really very useful is that because they have metal hydride, they weigh a lot. Most of them, the actual storage vessels, only a couple weight percent hydrogen compared to the rest of the storage system. But in a forklift, you need mass to hold that there. So it was early. There were studies. There were forklifts that went beyond demonstrations. I haven't followed whether any are still being used or not, but.
All of Walmart's distribution centers are
Yeah.
all hydrogen-powered forklifts.
Okay, those are the kind of forklifts. Those are exactly what they are. So now I'm taking a little break from that and going to the nickel metal hydride battery that I alluded to. These are actually the most commercial of any hydrogen hydride product. They were discovered in the late 60s, optimized 80s and 90s, and then put on the market. And so in recent years, these are the different battery sources, which didn't show it on this chart, maybe it got buried in there. But I believe the blue ones are the fraction of the, yeah, here's the color, red. So nickel metal hydride battery here. And so they are major, and they're in many of the hybrid vehicles because they have good operating principles. They're very robust. And they work by exchange. Reaction is you have a nickel hydroxide reacting with the metal, whatever the metal alloy is, and when it charges, it forms this oxyhydride, and the hydride, you discharge it, the hydrogen comes out. And so the metal hydride is the anode, and it goes back to this chemical reaction, and the cathode is this nickel hydroxide in a potassium hydrate electrolyte. And as you charge and discharge, you go, and these can charge, discharge for thousands of cycles with very small changes. And a number of alloys have been looked at. Early ones were called AB5s, a rare earth-based alloy, but then there's AB2s, and which are another type of cubic alloy. Some have high capacity, but they've been looking at one, magnesium one, that was an attractive one, but it had poor cycle life. But so these are just some examples of small batteries and larger batteries that actually went into vehicles. So nickel metal hydride batteries are in lots of consumer electronics. So whether they've virtually replaced the nickel cadmium batteries of the time, and while lithium oxide batteries are also used a lot. These are still used in a number of situations. And of course the all-electric vehicles use them, and some of the hybrids use the nickel metal hydride battery. So that's kind of how it's used, but what I'm going to do now is kind of take you through a little time journey about how hydrogen's been used over literally the decades. And hydrogen was actually used in a civil war to lift balloons up. And they would take a metal and dissolve it and get an acid, and you would release hydrogen gas that would fill a balloon, and it would go up because hydrogen has H2, has much lighter density. So it's like, you know, the guys that would take pictures of the battlefield and go, they use hydrogen-filled balloons. Wasn't mass transportation, but and also during World War I, the Germans had hydrogen-filled called Zeppelins, and they carried machine guns, but and they were used early on in the war, and they compared to other aircraft. The trouble was they're very big, and they're filled with the gas inside, so you start punching holes in them. They didn't last long, but they were used in the early part of the war, and they would arrive fairly quietly, so they were stealthy. But it was said that in the 52 raids, over 500 people were killed from the bombs and so forth that were dropped by the Zeppelins. The Germans liked it and actually put it in transport in the 20s, and they were the Hindenburg. So they used them for almost 2 decades until, of course, the famous or infamous crash of the Hindenburg out in New Jersey in '37. It killed 35 people in the airship, but 62 actually survived. It came down, but it was actually live coverage of it going down, which kind of ended the idea of hydrogen-fueled aircraft. But they did use it in World War II, again, to make surveillance balloons, weather balloons, and so they would use hydrolysis of a hydride, calcium hydride, wrecked water, and you would create the hydrogen. So here's a picture of them, and they would have a weather blue go up, they would put the hydrogen in, they would take visual, make sense, reading the weather. And so it wasn't forgotten, but again, in 1966, GM actually had the first hydrogen fuel cell powered vehicle. They took one of their vans, electro van, and they used cryogenic tanks of liquid hydrogen and liquid oxygen, just like rocket ships. Smaller, but just like a rocket ship. And they used an alkaline fuel cell, very similar to the one NASA. And it would work. It had a range there. So here's a cross-section of the van. You got the liquid oxygen tank here beside that. There was a report that one of the liquid hydrogen tanks actually exploded. They didn't do much more with that after that. So that one of the big concerns of using liquid hydrogen is just that. But there was a new boost that came in the early 70s. That's the oil embargo. I think most of you must remember when the price of gasoline went from 25 or 30 cents a gallon to 60 cents a gallon. And we were looking for any alternative to do that. And so the Atomic Energy Commission started opening or introducing that for solicitation for basic work. And so as a way to find alternative non-gasoline, non-petroleum fuel. And this is a magazine, Popular Science. It had, hydrogen will be the prime answer for air pollution and energy. You get clean hydrogen, you get no fossil fuel, and you could do atomic energy and do that, and you could burn it in an engine, or you use a fuel cell. So there were all kinds of examples of being touted. So again, there was a lot of optimism. You can see this is the, you probably can't see very well, but that's the electro van they were in this, described in this article. In fact, what happened was they reorganized the Atomic Energy Commission, they consolidated with others and formed the Department of Energy in 1975. And I was working at Mound, and we submitted a proposal to the Department of Energy. We got funded, and to start looking at some fundamental properties. It was basic energy science, and so we did crystal structure and composition, and electronic structure of hydride, and dopants and things. And we weren't looking at application, but we were looking at the mechanism, and we interacted with lots of outside organizations for over a decade, and our work in collaboration with other groups led to 45 peer-reviewed publications in journals and conference proceedings up through the early 90s. It took a while, some of them, to get published and reported, but it did. And so now with Hydrides, they were also doing demonstrations starting in the 90s, where you would have a hydride bed, a storage bed here. You would feed gas to a control unit. It would go in the fuel cell, and that fuel cell would then provide power to load to give you motion, and then you emit water. And the fuel cell waste heat provides heat to the hydride bed because the desorption of hydrogen is endothermic, and you need to warm it back up, and then they would absorb it with hydrogen. And so these are different hydrogen tanks. This is a little this was done at Savannah River, little tractor, gator, and here's their hydride tanks for that. This is a mine tractor, I don't forget. But again, these were situations where you could use a fuel cell, use hydrogen, it would last longer than a battery, you could do things with it. And at that time, it was also found that you could make stealthy submarines without using nuclear energy. You could use a fuel cell. It's not noisy, it's not much temperature because the fuel cell reacts low, and you could store, and because you have a submarine that needs a ballast, you can use a metal hydride to store your hydrogen that you need. And several European countries started looking at it. I'll show a little more in a bit.
You have that listed as, oh, maybe it's here.
What?
I was going to ask you probably what's on this chart.
Yep.
Okay. I wondered what made it hybrid. Now you've told me.
Yeah. So you use a titanium manganese alloy that would store hydrogen, and they had liquid oxygen, and they consume heat. They ordered 4 and they completed 1, and they're currently, as of 24, in the German and Italian navies, and a couple more are being floated around in Europe because they operate well. I haven't been tracking the literature very closely these days, but and so this is actually some photographs, and that's that picture again of the hydride storage tanks that go down in here and how they operate in ocean seas. So, but there's also been a large number of other types of maritime ships, big ones, small ones. They've been looked at starting back in 2000. The ones with stars are ones that actually use the metal hydride bed to store the hydrogen. The other ones use mostly gaseous hydrogen. A couple looked at liquid hydrogen, but most of them were compressed gas. And so this is from a recent review showing that there's still continued interest, and there's talk about building some larger ships out of that. But this is one that, one of the first ones, about 2007, that was done in England. It was like a canal boat. And they used a titanium iron, and they would have a 200-kilometer range, and they tested it for 3 or 4 years, and so that's actually an example of a nice, quiet. But as things went on, after about 20 years, I mean, in the United States, that early work that we did in the 70s and 80s, it kind of died down. Alternative things, looked at. Hydrogen kind of went back, but then there was a new program to address all the issues of hydrogen, and it was the National Hydrogen Storage Project, looking at ways. It was an integrated program out of the ER&E, and they formed 3 centers of excellence starting in 2005 on metal hydrides, the chemical hydride, and the high absorption ones. And they had an engineering center that started a little later, an integrated model. So the United States was doing that, and in that decade, they spent about $2.5 billion on hydrogen hydride technology. And they did result indirectly in some fuel cell cars that were internationally done. They ran them different ways. The Mercedes fuel cell vehicles, different one. But they were produced for specialized. In fact, you were able to buy a hydrogen fuel cell car in California. The challenge was, where were you going to get the gas and fuel, how you were going to go? And that's one of the real issues with having a vehicle, is getting places to get fuel. If you didn't travel very far. So fleets are more attractive to actually use when you're in an early stage of technology. And there were some of that done. But and that's where we mentioned about the forklifts before. And it was utilized, and it was also done in Europe. And these are some examples that were shown as a forklift, and the hydride tanks where they could control them. And now, DOE was going to give a boost to hydrogen technology. And they passed the Bipartisan Infrastructure Law and the Inflation Reduction Act in the early 1920s. And there was going to be hydrogen reduction, clean energy tax reduction, and tax credits, and all kinds of good things. And there was going to be a number of programs, and research and development, technology integration, demos were going to be started, and there were also going to be regional hubs, places where the whole integrated package could be explored and worked out. And so the intent was to go from this early phases of the stuff to the next model that could then presumably transition. And so these were the projects that were kind of scattered all over the United States were planned to be with hydrogen pipelines and all kinds of Texas and Midwest. There were even a couple here in Ohio with fuel cell buses and cars and all kinds of other gadgets. But then something happened. Donald Trump got elected. And when he took office, there was a big change. And the shift went completely away from renewable and hydrogen in particular. And they went to fossil fuel. Whatever hydrogen work was with fossil fuel, and they were doing that. And just 2 weeks ago, DOE announced that there were 223 renewable energy projects, including 2 of those hydrogen hubs. There were 6 on the drawing board. 2 were already. They happen to be in Portland, or in Oregon and California, Democratic states. They were cut. The administration said, well, these were inefficient, and so we're going to save taxpayer money by canceling the program. So at the moment, it's kind of bleak again for hydrogen. Well, what will happen in the future? I don't really know. So will the hydrogen fuel cell car come? This is a BMW at a gas station there. I actually spent 3 months in Germany consulting with a German research organization, and they had a hydrogen fuel cell car on campus, and I got to ride in it several times and do that. And Germany also instituted a hydrogen fuel cell train that ran a route, and I rode it a few times. I probably should have put a couple slides in, but it was kind of neat, and it was going to be the way of the future. But so there are practical hydrogen storage systems that are feasible. Buses, taxis, and maybe train, where they go between fixed points routes, and you don't have to build a complicated infrastructure. And because the real problem with passenger vehicle, not only is the amount of hydrogen that you can carry and the size it takes, but where do you fill it up? And you have to build that infrastructure and transport that. And most of the fuel systems are very hard to optimize all targets. You gain advantage in volume density, you lose something in mass, it weighs too much, or you have to control other features. And there's no material that can, a hydride that can meet all the properties that are desired. But for specialized things like forklifts, they are viable. Compressed gas, while it has its downside, 700 bar, is viable for tanks, and there are some. Now, cryo-compressed ones, these are possible. You don't go to liquid hydrogen, you use adsorption onto liquid nitrogen, so it's not as cold. But again, that's another challenge. There's a new book coming out. It was supposed to be coming out this month. Now there's 20 chapters on metal hydride technology. I wrote a chapter on metal dirigibles and tritides, which is not covered here, but I also contributed to a chapter on hydrogen hydride compressors. But anyway, there is a new book summarizing a lot of the work that's been done in the last 25 to 30 years. So when it comes out, I can let people know, and maybe you can get some for your leisure reading and think about the future. And thank you for your attention. So, any particular questions? Oh, good, everybody's asleep. Yes?
Bob, I've been reading that Toyota is now favoring hydrogen.
Yes.
vehicles. What technology are they using, do you know?
They use primarily gaseous storage fuel cell, but they have looked at a number of hydride options over the years. And I think they've actually gone to some larger, like trucks and so forth, to do that. So Toyota still, has their foot in the game, to do that. So it's just that it seems very hard to do. Again, hydrogen would work better when you localize your resources, so you don't have to solve and optimize all processes at the same time. Yes?
So Bob, are they storing the hydrogen in a metal tank, or a composite tank?
Um,
Vehicles like Mike was talking about.
They're in a composite tank.
Okay, does the hydrogen diffuse out? Is that an issue?
Yeah, but I do understand, but these are, hydrogen not very permeable in these particular polymers. So you know it's very high pressure and they're wrapped for stress. But these, hydrogen doesn't diffuse out of the polymers that they use now, or a very small amount. There are type 3 that have metal that would prevent that, but there's a weight problem. So, and hydrides, they virtually all use metal because you're holding heavier material, and you want good heat transfer in and out for thermal control of the hydride, because it releases heat when it absorbs hydrogen and cools when it desorbs hydrogen. So you need to either put heat in from some source, like from the fuel cell or elsewhere, to drive the hydrogen out, provide pressure, and to remove the heat when you're filling it up so it'll store the maximum capacity.
So,
Yeah.
so I think Japan is trying to go to more to a hydrogen economy, but they're getting their hydrogen from the Middle East. And
Yeah.
my understanding is they're exploring the idea of transporting hydrogen from the Middle East to Japan as ammonia,
Yeah.
and then taking and extracting the hydrogen.
Yes.
from the ammonia.
That is one of the options for doing. There's also work in Australia where they're looking at using a sodium boride hydride, because Australia would produce it by clean air. They have lots of solar power, and so they're looking at doing it, and with Japan and has a market for that, and other Asian, like Malaysia and a couple others. So.
And also, I think they're looking at either a cyclohexene or a
Yeah. Yeah,
or
there is a couple
toluene-based.
that will form or absorb, and then at relatively, with a catalyst at relatively low temperature, release hydrogen.
Right.
Again, there's a weight penalty in what you trade offers, and those are the issues. But in trading off costs and all the other
It's just
stuff.
a safety issue, I think.
And there is a safety, but again, you know, all depends, you know, what you call safe. But I'm pretty sure rocket fuel stuff is not. 700 bar hydrogen with a little hole is not going to be particularly safe. And yes,
You showed on some of your characteristic curves some hysteresis. You also showed a 3D array of the metal, what I think was the metal ions, and how the hydrogen ended up
Yeah.
in that array
yeah,
with the growth in volume.
yeah.
What is the, in those beds that you've described, what's the nature of the hydride? Is this a finely divided material? Is it something on a substrate? Is it porous solid? What is it?
There can be different ones, but a metal hydride is basically a powder.
Okay.
So that theoretical density that you say about a single crystal is really a lot lower than that.
Understood.
And so that's part of the challenge is, okay, it was really great, but you have to you make the powder because it does expand and contract. And it also allows that you can put thermal conducting additives in sometimes too that would help to heat transfer. So there are ways, I mean, we did that on, you know, some of our, on our spacecraft work that we did on our core.
Does that volume change of the material contribute to a life-limiting factor through strain?
Normally not.
Okay.
I mean, you have, you know, it's a trade-off in design of having sufficient space and what they change, but it can happen.
You might describe the aluminum foam as
Yeah.
to answer
Right,
part of
if
his
you use,
question.
we put it into aluminum foam matrix, and therefore that would hold it pretty much in space and would expand and contract and conduct very well. The thing is, aluminum foam is very pricey, particularly if you scale to large stuff. So it now makes it too expensive. Okay, well, I thank you for coming, and
Well, thanks a lot,
You bet.
Bob.